Section 3.2 is about polynomials and the graphs. So in 3.2 additional practice, we've already gone through the lesson and we just want to make sure we do several problems to make sure we have mastered all of the concepts we learned from the lesson. So in order to graph a polynomial, we're going to need to use the leading coefficient test to determine the end behavior. We'll find the x-intercepts, or otherwise called the zeros. Then we'll need to find the multiplicity of each zero and state whether the graph crosses the x-axis or touches and turns at each of those zeros. For a little additional information, we'll find the y-intercept. It will be worthwhile just to state if the graph has any symmetry, that is to say, is it even, odd, or if there's no symmetry, or because it's not even nor odd. And then to graph the polynomial. And again, remember that the graph of a polynomial is smooth and continuous. So with all of that, we'll get a fairly accurate polynomial. There's a few things that we can't figure out at this point, namely the maximum and minimums, the ups and the valleys and the peaks in the middle. We need something known as the derivative, and that's typically taught in the calculus course. So we have a little bit of ambiguity in our answers, but we're still just going to focus on these 5 things stated in the directions. So let's go through this a problem at a time, and hopefully you get all the ideas. All right, number 1. We are given this polynomial in factored form. That is to say, if we wanted to multiply this all out, we could. So you could just have like the x plus 2 times x plus 2, FOIL that out, and then the x minus 7 and distribute that. So we don't actually need to do that. We can get all of that information just from the fact that all the information above in the factored form. So the first thing we'll go ahead and do is figure out the degree. The degree in this case, you kind of have to, there's 2 ways to go about it. You could think about it as the sum of the multiplicities, which we haven't done yet. But the multiplicities comes from the exponents. So the fact that we have a 2 and a 1, that means that the degree is going to be 3. You also could think if we multiplied all of this out, we would end up with an x cubed first and a bunch of other things that follow it. But the degree of 3 is what we'll need for the leading coefficient test. We'll then also figure out the leading coefficient. The leading coefficient is going to be the number in front, so in that case it's just the number 1. So we have an odd degreed polynomial with a positive leading coefficient. When you put these 2 ideas together, what we could go ahead and state is that the end behavior is, well, opposite because it's odd. We go down to the left and up to the right. So when all is said and done, we'll have a graph that essentially has end behavior like shown in the temporary highlighter. All right, so now we need to find the x-intercepts, or the zeros. Well, in factored form, it's pretty easy. The zeros here are just going to be coming from each factor. And of course, if you take like the x plus 2, set that equal to 0, you would subtract 2 from both sides. So our first 0 is going to be minus 2. Our second 0 is going to be the positive 7 coming from this factor. Now, each 0 has a multiplicity that says how many times that 0 occurs. So the multiplicity, I'll just do multi for short. So we need to figure out where this negative 2 came from was this factor, and that factor occurred twice. So the multiplicity of negative 2 is 2. And the multiplicity of 7, well, is going to be 1. So now that we have the multiplicity, we can think about the behavior. So let's go and put the zeros. So negative 2 would be right here. Positive 7 would be over here. We know that there will be an arrow going over to the up to the right and down to the left. So we need to, with that, you actually, as you go through and do the work here in the middle, you want to make sure that those all align. So the multiplicity whenever the multiplicity is, I'm going to change my color here and zoom in just to focus on it. Whenever the multiplicity is an even number, so again, this 2 is an even number, so we can say that the behavior at the x-axis is going to behave like a parabola. So that is to say it's going to touch and turn. I'll go ahead and probably shorten this to TNT, or for TNT, touch and turn, for the remainder of the lesson, but just to state it up front. Then 1 is an odd number. Because 1 is an odd number, it's going to behave like the cubic graph. That is to say it's going to cross at the x-axis. So zooming back out, what will happen is we go ahead and connect these, but let's just kind of focus. It's going to touch and turn there, and then it's going to cross up through here. The last bit of information we want to go ahead and state for the graph is going to be its y-intercept. So the y-intercept here, you just plug in 0. So you end up with a 0 plus 2 squared times 0 minus 7, which is going to give you a 4 times minus 7, or minus 28. So the y-intercept is just somewhere down here. We don't need a perfect graph, so we'll just kind of put some dots and we'll just say minus 28. So to go ahead and complete the graph, we could also state if there's any symmetry. And in the case of symmetry, that is when the function's either even or odd. So even is when all of the exponents are going to be even degreed. Odd when they're all odd degrees, and if they're mixed, then there won't be any sort of symmetry. And this one's a little bit hard to see in its factored form, but if you were to FOIL it out, you would have like an x cubed, then you would also end up with an x squared, you would have an x term and some sort of constant term. So the fact that you have even or odd terms means that there would be no symmetry here. With all of that, we don't have to worry about the symmetry, so I'm going to start from the left of my graph. I'll go ahead and come up. I'll touch and turn as stated in that green part from the x-axis behavior. I'm going to go down here. I'm going to go ahead and touch. I'm going to go through the intercept. Again, I don't really know where this maximum, or in this case minimum, is, so I'm just going to go ahead and just make it wherever we feel like it, and then we'll go back up. We'll cross through the x-axis for the x-intercept, and then we'll connect to the other piece of the end behavior. So there is the first one. If you want to go ahead and check our answer, there's a couple things I noticed about this. So you can see right here our answers. This basically goes down, and we don't know what's happening off here, but you could, again, the minus 28's down there. And don't get thrown off by the fact that the x-intercept is given as an ordered pair. Notice that those are the same values that we got earlier, and then the y-intercept is, of course, the minus 28. So now that I've done a basic example, kind of just going through it pretty slowly, there's 8 of them, so I'm going to speed up just a little bit to go ahead and do several examples. All right. So number 2, the degree here, well, is the sum of the multiplicities, which is going to be 2. Well, I'm going to write it like this. So 2, 1, and 1. So it's going to be a degree of 4. The leading coefficient is the number in front. For the sake of this course, I'll never try to hide it inside one of the factors. But the leading coefficient is, in this case, 1. So an even degreed polynomial that has a positive leading coefficient will give us the end behavior that is the same because it's even, and opening up because it's positive. The zeros here in factored form is pretty easy. If you set the x squared equal to 0, that's going to give you a 0 of 0. So I'm going to go ahead and put these in order. So the smallest 0 is going to be the minus 4 from the last factor, 0 from the x squared out in front, and a positive 6 from the middle factor. To find the multiplicities of each of these, well, look at the numbers on the exponent. So both 1 and 6 have a multiplicity of 1. excuse me, I misspoke there. Both negative 4 and positive 6 have a multiplicity of 1, and 0 has a multiplicity of 2. Because of the even and oddness of the multiplicity, we can say it crosses at negative 4, it touches and turns at 0, and it crosses at positive 6. The y-intercept here is going to be, well, let's plug in 0, and we'll have 0 squared times 0 minus 6 times 0 plus 4, which is just going to be 0 because of that 0 in front. And again, like above, there's no symmetry. If you were to FOIL all of that out, you would have mixed exponents on the variable. So putting all this together, let's put our zeros first. That makes it easier to figure out where to put the end behavior. So negative 4, 0, and 6. We know that the end behavior is going to be opening up, so rising to the left and the right. At negative 4, we're going to cross. At 0, we're going to touch and turn. And at positive 6, we're going to cross. We have just that one y-intercept is 0, so let's go ahead and connect these pieces. I am going to be intentional to not make it symmetric. I don't really know where those minimums are, so I'm not going to stress about putting it at a certain spot, but there's the answer for number 2. Number 3, again, is going to be in factored form. Are these all in factored form? No, we get some fun ones down below. All right, so number 3, the degree here is the sum of the multiplicities, or if you FOILed this out, you would have a cubic term in front. The leading coefficient is a positive 1, so the fact that this is odd with a positive leading coefficient will tell us that our end behavior here is going to be down to the left and up to the right. The zeros, again, fairly straightforward in factored form, which are just going to be putting them in order. Minus 8 from this factor, minus 3 from the first, and minus 1 from the middle. In the case of the multiplicity, the factors have an exponent of 1. So the behavior at the x-axis for each of these zeros is that it'll cross. The y-intercept, we plug in 0. So again, we're using h of 0 here because it's just named a little bit different. Is going to be 3 times 1 times 8. Again, plugging in 0 doesn't change the addition. So we have 24 as the y-intercept. No symmetry for the same reason as the ones before. So let's go ahead and put that information. So negative 8, negative 3, and negative 1 are my intercepts. Put those. Again, the 24, the y-intercept's up here somewhere. So I'll just go ahead and add some dots and just say, hey, go up here. And we're going to go down to the left and up to the right. And again, to really get this correct, I'm going to have it way up there so that it goes through the y-intercept. And it crosses at each point. So it'll go up, it'll come back down, it'll go back up. And again, it's kind of hard to get this exactly right with my handwriting and the scale, but hopefully that does a good job of capturing the smooth continuous curve of a polynomial. So there's number 3. Number 4 is going to have, so it's going to be j of x, so it's named with j. So the degree here is, again, the sum of the multiplicities. So x to the 1, the x plus 5, and the x minus 5, so it's all 1s. So the degree here is 3. The leading coefficient this time is going to be a negative 1 because of that negative in front. So an odd degreed polynomial with a negative leading coefficient. It will reflect the initial arrows over the x-axis, so it's going to be up to the left and down to the right. The zeros here are going to be negative 5, 0, and 5. This middle term gives me, when I set that equal to 0, gives me the negative 5. The minus x gives me 0, and the x minus 5 gives me, over there, the positive 5. The multiplicity here is 1 in each case. They are all odd, so the behavior at the x-axis is that it'll cross at each of the given zeros. The y-intercept here, when you plug in 0, because of that 0 in front, is just going to be 0, so I'll just save myself some writing. And again, there's no symmetry here. To verify that there's no symmetry, let me go ahead and maybe this one's pretty reasonable, so I'll, well, actually, is there symmetry here? Let's go ahead and do it. So let me go ahead and check this. If I were to multiply this out, what I would end up with is a minus x times an x squared minus 25. Okay, so if we then, again, the middle terms cancel, distribute, we end up with a minus x cubed minus a minus is a positive 25x. Oh, I'm glad I checked this. So let's go ahead and backtrack a little bit. There is symmetry here. Because if you look at this is an x to the third, and then this is, I forgot to write the x, so let's go back here. So there's an x right there, and then this is an x to the 1. All of those exponents are odd, so we have an odd polynomial, which has symmetry over the origin. Okay, so let's see what this looks like now. So we have -5, 0, and 5. The y-intercept is 0, and we have end behavior that rises to the left and ends to the right. So we're going to go ahead and go down, and this is where it's going to be a little bit tricky because to keep the symmetry, but we're going to go down. And again, I don't know the mins, but I'm going to just go ahead and kind of try to put it right there in the middle, right at 2. So when I go up, I need to make sure that in the first quadrant, I have that same hump just in the first quadrant. So it's going to look something like this. On the test, don't stress too much about it being exact if you have to graph, but just to do this problem justice, let's go ahead and look at the graph in the answer key and see if it looks well. And it doesn't really look that great because the minimums and the maximums are like way off where we at. But again, to figure this out, it's impossible with our current tools. Well, not impossible. We just have to plug in a lot of points. So let's go ahead and slide back up and do a few the other 4 examples. These are going to be in the expanded form. All right, so number 5. The degree of this one is now just the highest power of x. So it's 4. The leading coefficient is just going to be 1. So an even degreed polynomial with a positive leading coefficient. Its end behavior is just going to rise to the left and rise to the right. The zeros are a little bit harder here. So we're going to have to take the x to the 4th minus 29x squared plus 100 and set it equal to 0. So what we'll need to do is find the values of, or the product, 2 numbers that multiply to 100 but add to -29. Well, those are going to be a minus 25 and a minus 4. And the thing to note is because this is a 4th and a squared, you'll end up putting an x squared here and x squared here. So when you FOIL, everything still is going to be the correct powers. These are difference of squares. So this could be factored further as an x plus 5 and x minus 5. And this is an x plus 2 and an x minus 2. So this is the fully factored form, which we could then find the zeros of x equal to minus 5, positive 5, minus 2, and positive 2. So returning to what we are working with the earlier examples, the zeros, I'm going to put them in order this time, are minus 5, minus 2, 2, and 5. The multiplicity, again, comes from the fact that all of these factors have a 1 on them. So the multiplicity for each of these is 1. And the behavior at the x-axis is that it crosses at every single one. So I'm going to just do CR for short, so I don't have to write that 4 times. The last thing to note is notice that it's easier to identify symmetry because here we have an x to the 4th, and here we have an x squared, and this is an x to the 0. So 0, 2, and 4 are all even, and an even graph or an even function has symmetry over the y-axis. Okay, so all of the setup is done. So our zeros are -5, -2, 2, and 5. Notice that those are symmetric. The end behavior rises to the left and rises to the right. And let's, I forgot the y-intercept. So the y-intercept, this will be a little out of order compared to the earlier ones. F of 0 is 0 to the 4th minus 29 times 0 squared plus 100. It's always easy in expanded form to get the y-intercept because everything cancels except for the 100. So the 100 is going to, again, be up there. All right, so let's keep this symmetric to the best of our ability. So I'll go down, I'll cross, I'll kind of take note of where I put my minimum, and I'm going to cross again. And to keep the symmetry, I actually know that the 100 is going to be where the maximum is. So I'm going to come back down. And again, a little bit tough here, just because I don't have this most steady hand. And we're just going to have this, and we'll go back up. So there's a semi-symmetric, a little shaky, but hopefully you notice the ideas of symmetry in play. Oh, that's why this is off. That needs to be over here. So let's fix that. So let's move that to 2. So that looks a little bit better, like so. There we go. All right, so hopefully everything there makes sense. If not, go ahead and rewind the video and get it again. Moving on to number 6. The factoring method here is a little bit different than the previous one because there's a common term, but here we go. The degree here is 5 is the highest power of x. The leading coefficient is a positive 4. So an odd degreed polynomial with a positive leading coefficient is going to be an end behavior that's odd, so it's opposite, so down to the left, up to the right. And again, emphasizing, just in case you haven't caught it yet, odd or even is the scenario for the degree. Positive or negative is the property for the leading coefficient. A degree will never be negative, so there's no point to even consider whether it's positive or negative because it'll always be positive based off of what we said at the beginning of 3.2's lesson. All right. To find the zeros, we'll take the 4x to the 5th minus 36x cubed, set it equal to 0. Notice that both of these numbers are divisible by x cubed. I'll factor that out in front, and I'll be left with 4x squared minus 36 equal to 0. That's actually a difference of squares. This is x cubed, and then this is going to be 2x plus 6 times 2x minus 6 equal to 0. Set each of these equal to 0. You get x equal to 0, x is equal to minus 3, and x is equal to positive 3. And as I mentioned earlier, I'm not going to hide the leading coefficient in the factors because notice that that 4 is actually hidden inside the factors here. But we now know our zeros. I'll reorder them. So it's minus 3, 0, and 3. In each case, the multiplicity is odd, but let's see, again, the 0 has a multiplicity of 3, so this will be 3, and these are both 1. But still, because they're all odd, the behavior at the x-axis is that it'll cross. So I'll just do CR for short. The h of 0, so let's find the y-intercept next, is h of 0 is going to be 0 because, again, plug in 0, everything cancels. And this is odd and this is odd. The powers are all odd. So we have, again, symmetry over the origin. So with all of this put together, our zeros are -3, 0, and 3. We have down to the left, up to the right, a 0 y-intercept. Keep symmetry, so we'll go up, we'll come back down, keeping that same kind of hump just in the fourth quadrant. Oh, let's try that again. In the fourth quadrant instead of the second. So let's try that again. There we go. And then we'll end to up to the right. So there's number 6. 2 more. Again, hopefully you're getting the hang of this. I would encourage you maybe to pause and just try these last 2 since they're very similar to the ones we did. But just for the sake of completion, let's go ahead and do them together. Again, 7 is an expanded form, so the degree is the highest power of x, which is 4. The leading coefficient, oh man, it would be nice if this one was negative just to get the whole variety, all of the variety, but if this was a negative leading coefficient, you would have opened it down. We just didn't have one of those in this practice, but I don't want to mess with things so the key matches. So the degree is 4. The leading coefficient is 1. So even degreed and a positive leading coefficient will tell me that the end behavior here is going to be up to the left and up to the right. Setting x to the fourth minus 16x squared equal to 0. Factor out the x squared and you get the x squared minus 4 equal to 0. Again, that x squared minus 4 is a difference of squares. If you aren't sure, you may just want to do a quick internet search to look at some additional examples or to go through the details of that. So this will be an x plus 2 and an x minus 2 equal to 0. So x will be equal to 0, minus 2, and positive 2. Those are my zeros, which I'll now go ahead and put in order as in minus 2, 0, and 2. The multiplicity of each of these are 1. Well, not quite. Oh, that's 1. This is 2. This is 1. Some variety here. So the behavior at the x-axis is that it's going to cross, touch and turn at 0, and cross again at 2. The y-intercept here, when you plug in 0, j of 0 is equal to 0. And again, because all of the powers on the x's are even, we do have symmetry that is over the y-axis. Putting all that together, I'm going to start with my intercepts, namely -2, 0, and positive 2. My end behavior is up to the left and up to the right. And as I draw this, I'm going to keep in mind that I'm going to cross here, touch and turn at 0, and cross through 2. So we'll go down. And again, this one needs to be symmetric, so I want to keep those the same minimum and go up. And that is sufficient for what we're able to do now. Let's take a look at number 7's answer key and see if we can see the symmetry any better here. And not really. Again, it looks like these minimums are probably closer to like negative, I don't know, maybe -20, -30. One more example, going back to the factored form. So the degree here is the sum of the multiplicities in factored form. So there's 3 x's here, 2 x's here, and 1 x from that, or 1 x for there. So 3 plus 2 plus 1 is going to give me 6. The leading coefficient is the number in front because I'm not hiding it in any of the factors. So it'll be 1. The degree is even. The leading coefficient is positive. So therefore the end behavior here is going to be up to the left and up to the right. In factored form, I can go right to finding or stating the zeros. Stating the zeros here, they're in order. -3 from the right here, 0 from right there, and a positive 7 when you change the sign. When you set it equal to 0. The multiplicity is going to be, well, 1 because of the exponent on the x plus 3, 3 because of the cube on the x, and 2 from the square on the x minus 7. So the behavior at the x-axis is going to be, let's see, because the 1 is odd. So just in case you haven't caught it yet. So last example, so I'm going to say it one more time. -3 has a multiplicity that is odd. So again, the odd is on the 1, so that is what's causing it to cross. 0 is an even number, but I don't care that 0 is even. It is 3 that is odd, so that is why it'll cross. 7 is an odd number, but I don't care that 7 is odd. 2 is an even number, so the multiplicity is even, is going to cause it to touch and turn. Zooming back out, let's finish this problem. The y-intercept is f of 0 will be 0 because that 0 cubed in front. And there's no symmetry here. If you were to FOIL all of that out, and you could even see that in the zeros, that they're kind of all over the place. So -3, 0, and 7. My end behavior is up to the left, up to the right. I'm going to cross at -3. I'm going to have to hit a minimum, and I'm going to have to cross back up at 0. And I'm going to touch and turn over here at 7, and just kind of putting that on the correct side. And the reason I knew it was going up is because I kind of know I'm going to cross, so I'll have to come back down. So now filling in the middles in that smooth continuous curve, we'll get a graph that looks like that. For, again, a more accurate one, we would need a graphing utility, which we don't use for the course, just so we're focusing on the properties, or the derivative, which is, of course, follows in Calculus 1. But 3.2 has a lot of information, so hopefully these examples helped you out. Practice and study hard, and reach out if you have any questions or need any help. Good luck.